922 7B 246 Quantum Fluctuations, Uncertainty Principle, Space-Time Wow Seti. There's the alien radio signal. And here's the data here. Okay, so I'm going to just make that a little bit smaller so it fits into the camera. And we'll go back this way a bit. Okay, so we're going to talk about quantized Klein Gordon field. I'm going to Google that. Vacuum state, density, configuration, Fourier transform, Gibbs probability, density, I'm going to Google that too. Non-zero temperature, ultra-cold atoms, Planck's constant, quantum kernel, quantum vacuum state, Lorentz invariant, classical continuous random field, Swartz space, I'm going to Google that, and this is keyword research, line 22. Wow data. So the keyword to Google was quantum fluctuations, which we'll be doing over the next several videos to find out what kind of research you guys have come up with for it. Quote wiki, quantum fluctuations of a field. A quantum fluctuation is the temporary appearance of energetic particles out of empty space, as allowed by the uncertainty principle. The uncertainty principle states that for a pair of conjugate variables such as position, momentum, and energy time, it is impossible to have a precisely determined value of each member of the pair at the same time. For example, a particle pair can pop out of the vacuum during a very short time interval. An extension is applicable to the uncertainty in time and uncertainty in energy, including the rest mass energy of mc squared. When the mass is very large like a macroscopic object, the uncertainties and thus the quantum effect become very small, and classical physics is applicable. This was proposed by scientist Adam Jonathan Davis, a study in 1916 at Harvard's laboratory in 1996. Davis's theory was later proven in the 1920s and became a law of quantum physics by Louis de Broglie. In quantum field theory, fields undergo quantum fluctuations. A reasonably clear distinction can be made between quantum fluctuations and thermal fluctuations of a quantum field, at least for a free field. For interacting fields, renormalization substantially complicates matters. For the quantized Klein Gordon field in the vacuum state, we can calculate the probability density that we would observe of configuration of those symbols and at a time t in terms of the Fourier transform with these symbols here to be this calculation here. In contrast, for the classical Klein Gordon field at non-zero temperature, the Gibbs probability density that we would observe a configuration of these symbols at a time t is, and again we have another set of functions there. The amplitude of quantum fluctuation is controlled by the amplitude of Planck's constant, and there's a symbol there, just as the amplitude of thermal fluctuations is controlled by a k and t. Note that the 3 points are closely related. Planck's constant has units of action instead of units of energy. The quantum kernel is, instead of the quantum kernel, is non-local from a classical heat kernel viewpoint, but it is local in the sense that it does not allow signals to be transmitted. The quantum vacuum state is Lorentz invariant, although not manifestly in the above, whereas the classical thermal state is not the classical dynamics and Lorentz invariant, but the Gibbs probability density is not a Lorentz invariant initial condition. We can construct a classical continuous random field that has the same probability density as the quantum vacuum state, so that the principal difference from quantum field theory is the measurement theory. Measurement in quantum theory is different from measurement for a classical continuous random field, in that classical measurements are always mutually compatible. In quantum mechanical terms, they always commute. Quantum effects that are consequences only of quantum fluctuations, not of substitutes of measurement incompatibility, can alternatively be models of classical continuous random fields. Data continues next video. Now you should make a game of saying classical continuous random fields really fast. Have fun.